When 200 tons of steel thunders down a track at speed, the laws of physics are pushed to their absolute limit. The momentum is unstoppable. The force is catastrophic. And often, the only thing standing between that rolling locomotive and total disaster is a single piece of misunderstood engineering. To the general public, it is a relic of the past, known by the romantic, almost cartoonish name, the Cowcatcher. We picture it on old Western movies, scooping up livestock with a gentle bump. But to the railroad engineers, the mechanics, and the train crews whose lives actually depend on it, that name is an insult. They know it by its true name, the pilot. This distinction is not merely semantic. It is a matter of function, physics, and survival. The pilot is not a basket designed to catch stray animals. It is a rigid, calculated wedge of armor designed for a singular, violent purpose, to clear a path through chaos. If you want to understand how a train survives a collision, you have to look past the romance. You have to look at the brutal engineering of the nose. This is the story of how a wooden wedge evolved into a steel ram, and how the shape of the train was dictated by the harsh realities of the American frontier, the blood sacrifice of brakemen, and the unforgiving laws of kinetic energy. To truly understand the pilot, we must first travel back to the environment that necessitated its invention. We have to look at mid-19th century America. At this time, the railroad was an intruder in a wild, unfenced world. In Europe, rail lines were often manicured, guarded, and fenced off from the countryside. But in America, the tracks cut through vast, open ranges. This was a world where cattle, bison, and wild horses wandered freely, completely unbothered by the distant whistle of a steam engine. In this unpredictable landscape, the steam locomotive was surprisingly vulnerable. It looked like a beast of iron, but its anatomy was fragile. The earliest engines carried their most critical machinery, the cylinders, the driving rods, and the delicate valve gears, mere inches from the ground, positioned right at the very front of the train. In this configuration, a collision with a single stray animal was not just a nuisance, it was a potential death sentence. If a 19th century locomotive struck a bison or a cow without protection, the animal's body could be rolled under the wheels. This would shatter the wooden frame, destroy the running gear, or worse, lift the front wheels entirely off the rails. If the lead wheels left the track, the engine, the crew, and every passenger car behind them would topple into disaster. The solution was the pilot. The early designs were iconic. We see them in black and white photographs, long, sweeping structures made of wood, reinforced with heavy iron straps. But this design wasn't an aesthetic choice, it was strictly functional. The geometry was deliberate. It featured a low slope designed to guide obstacles down toward the ground, while the wedge shape pushed them violently to the side. Notice the construction. They were built with slats. This open, slatted design wasn't just to save weight, it prevented the pilot from becoming a solid wall. If the pilot were solid, it might trap a body or debris against the front of the train, increasing the friction and the risk of derailment. The slats ensured that nothing stuck. The goal was never to catch anything. The goal was to deflect danger before it could reach the wheels. On the open range, the pilot's job was to adapt to the land. It provided a gentle nudge, relatively speaking, to clear a path through the biological hazards of the frontier, sparing the machinery and the men behind it. By the 1870s, the design of the locomotive's front end faced a new pressure, but this pressure didn't come from the track ahead, it came from the connection between the cars. For decades, the standard method for connecting train cars was a nightmare known as the link and pin system. This crude setup required a human being, a brakeman, to stand dangerously in the gap between two moving cars. As the cars crashed together, he had to manually guide a heavy metal link into a slot and drop a pin to lock it in place. To accommodate a human standing in that crush zone, there had to be a significant gap between the locomotive and the first car. This gap was deadly. It was a terrifying space where one slip meant death. Every single year, thousands of railroad workers suffered crushed hands, mangled limbs, or were killed outright. However, from an engineering point of view, this wide spacing inadvertently allowed for the continued use of those long, dramatic, sweeping wooden pilots. There was plenty of room for them. The paradigm shifted thanks to a man named Eli H. Janney, a former Confederate officer turned dry goods clerk. He patented the Knuckle Coupler in 1873. His invention was brilliant in its simplicity. It mimicked the hooking of two human hands, and crucially, it locked automatically on impact. The impact of this invention was twofold. First, it meant men no longer had to stand between the cars to couple them, but the trade-off was spatial. The new coupler was shorter, stronger, and required a much tighter fit between the engine and the car. Suddenly, the geometry of safety had shifted. There was simply no room left for the long, protruding wooden pilot. Change, however, was slow, until the government stepped in. In 1893, Congress passed the Safety Appliance Act. The hearings were filled with horror stories of the Lincoln Pin era. The act mandated automatic couplers and air brakes for all interstate railroads. This law saved thousands of lives, but it also forced a total redesign of the locomotive. The theatrical, long-nosed wooden pilots were now obsolete. In their place, a new, compact, and far stronger design was required. The era of the nudge was over. The era of the steel shield began. As the 20th century dawned, trains became heavier, faster, and more powerful. The gentle deflection offered by wood was no longer sufficient. The new pilots were forged in the language of the Industrial Revolution: steel. Railroad workshops were places of frugality and ingenuity. Mechanics often built these new pilots from the bones of the engines themselves. They would take discarded boiler tubes, cut them down, clean them, and weld them into dense grid frameworks. These cylindrical forms were incredibly strong, naturally braced to absorb the shock of whatever the rails delivered. On the faster passenger lines, railroads began using pilots cast from a single piece of solid steel. These were massive, seamless, and brutally overbuilt. They were engineered to withstand strikes at speeds nearing 100 miles per hour. The design philosophy had evolved into a wager against disaster. The steel pilot became a form of sacrificial armor. The logic was simple: better to break the nose than lose the train. A bent bar could be straightened in the shop. A cracked plate could be welded. These repairs were trivial compared to the alternative: a shattered cylinder, a destroyed frame, or a derailed train lying in a ditch. If you visit a railroad museum today, take a close look at the front of the locomotives. You will often see the scars of this brutal calculus. You will see dents in the steel face, patches riveted over torn metal, and bars that are slightly warped. These are the silent records of impacts with rocks, logs, and automobiles. Every scar represents a moment where the pilot took the blow so the train could return home. Part 4. The physics of the crash. But the true genius of the pilot isn't just in its material. It is in how it manages the terrifying physics of a collision. Let's visualize a standard freight scenario. Imagine a 200-ton locomotive traveling at 35 miles per hour. In terms of kinetic energy, this train carries the equivalent force of a fully loaded semi-truck dropped from the roof of a 5-story building. Now, imagine a rock, dense and immovable, sitting squarely on the rail. When the collision occurs, it is not a slow event. It is a negotiation between mass and speed that happens in milliseconds. First, the impact. The sloped face of the pilot strikes the rock. It does not try to catch it or cradle it. It delivers a sharp downward blow. The angle forces the obstacle down into the ballast, the gravel bed, or ejects it violently to the side. Second, the absorption. The force travels instantly from the face of the pilot to the pilot beam, a heavy transverse structural member sitting just behind the nose. This beam is designed to absorb the initial shock. It acts as a buffer. It may bend, but it must hold firm. Third, the anchoring. The load then flows into the locomotive's main frame. The immense weight of the engine presses down, anchoring the structure to the rails. This downward pressure is vital to prevent the train from vaulting over the obstacle. Finally, the stabilization. The pilot truck, that swiveling set of small wheels at the very front, reacts instantly. Its springs compress, distributing the trawa across the rails and preventing the locomotive from twisting or lifting off the track. If the engineering holds true, if the geometry is right, the beam is strong enough, and the truck is aligned, the locomotive rides over the debris. The wheels stay guided by the rails. The kinetic energy is managed, transforming a potential derailment into nothing more than a repairable dent. Conclusion: the unseen shield. The pilot is a testament to a simple reality. Progress in engineering is often measured by the disasters that don't happen. From the wooden slats that navigated the bison herds of the Wild West to the cast steel rams of the modern era, the function has remained unchanged. It is a device born of hard-won experience and tragic lessons. It represents a brutal logic: deflect, survive, keep moving. Today, as high-speed trains slice through the landscape, the pilot remains. It is usually sleeker now, hidden behind aerodynamic cowlings to reduce drag, but beneath the skin, the steel skeleton waits. It remains the first and last line of defense, the brutal engineering that ensures the journey continues.